So good morning. Nice to see you all online and in person here at our EPFL CIS Digital Twin Days. It's my big pleasure to welcome you in the name of the organizing committee. When we started discussing this event, we thought it would be great to invite speakers from academia and from industry to show us how they work on digital twins and what they are working on. So today is the first day where we'll have 4 presentations from renowned professors of the field. And tomorrow we'll have 3 presentations and a panel discussions more geared towards the industry. We wish you fantastic 2 days, either online or with us here at the Swiss Tech Convention Center at EPFL. And now without further ado, I ask Pierre please to come up and introduce our first speaker.
Thank you, Jan. Thanks all for being here this morning, here or online. And it's a pleasure to welcome our first speaker this morning, Professor Eleni Chatzi. Eleni is from our sister school, ETH Zürich, where she holds the chair of structural mechanics and monitoring. She's been with ETH as soon as she finished her PhD from Columbia University. She has received far too many accolades for me to list in this very short introduction, but I do have to mention her recently being honored with the Walter L. Huber Civil Engineering Research Prize, because that's one of the most important in the field. And this morning she's going to give a talk on the synergy of data and models for virtualizing structures and infrastructure. So right, spot on for the theme. Thanks, Eleni.
Thank you very much for the introduction and for the invitation to come here. It was a train ride, but still, you know, it's odd to be somewhere in presence to give a presentation, and I feel very much excited for this. So as mentioned, today I will be discussing this synergetic use of data and models for virtualizing structures, or essentially for rendering these digital representations that are also called digital twins. And maybe just to give a bit of background as to why this is relevant for my field in civil engineering, this is largely because structures are not necessarily the passive and inanimate objects that we typically think of them as. Instead, they are living and breathing organisms that experience motion, injury, accidents, they age and deteriorate. And of course, together with this, they also compromise the important resources that they host. And so the question is how to deal with this kind of a problem, which is very real in developed societies these days. And for us in our group, the answer is sought through the concept of structural health monitoring. And structural health monitoring is essentially the utilization of sensoric that is typically of low cost and that is deployed on structural systems for understanding behavior, for understanding the response of these systems, for diagnosing their current performance and condition, and for prognosing their remaining useful life and performance, allowing us to take decisions that could optimize their management. So this structural health monitoring chain, as I call it, is essentially one that comprises 4 main stages. First of all, the acquisition of data that could come at various forms. I already explained that in a civil engineering context, we're dealing with large structures, and so we prefer to use low-cost technologies that are, however, mature enough to provide information at the level of precision that is required for understanding the performance of these systems. I will more discuss today why data is not enough, and so typically we need to boost the information that comes from sensors with some meaningful interpretation that could be derived from simulations or models of the system. And we do this in order to be able to extract indicators of performance that are essentially quantifiable metrics of how these systems perform. And we would like these to be robust and impartial to the degree feasible, but also explainable. And then finally, we're able to do this on a number of systems or a population of structures, or you may call them fleets. Then we're able to understand and generalize our conclusions and support decision at that level, at the level of the population. So today I will more focus on the aspect of simulation, which is also more of what I consider critical for virtualizing systems. But as I explained, since we deal with this whole cycle, I would first also like to explain why in another stream of our work, we're also looking to extract the most that we can from data. So without necessarily including a model of the system. So I only have 1 slide on that, but data is also in itself very powerful. In fact, it can take you in places that models cannot currently take you. So for this, I show you one example, again, of monitoring. In our case, for wind turbine infrastructure, where you see the wake effect, which is a phenomenon that is not necessarily very easily captured by computational fluid dynamics models or other types of simulations. And so in this project, we set out to use data that is readily available for wind farms to try and derive models of the interaction of turbines with each other, this wake effect that is caused by the orientation and situation, the placement of turbines within a farm. And indeed, it is possible to actually extract information that, again, is purely derived from data and that explains the way in which a turbine is fatigued, so you can extract engineering metrics that come just from the processing of these collection of SCADA information. And we do this by extracting or deriving generative models using conditional variational autoencoders in this case. But nowhere in here is some sort of bias, inductive bias of what a model would have done to give you this info. But of course, this is not always meaningful. In this case, we had to do it, and we're glad that it worked. But in most cases, at least for engineering assessment, data is not in its own enough. These purely data-driven representations are oftentimes good for giving you information on the level of diagnosis, so understanding what might be wrong with the system. But the moment you want to understand something more and prognose how the system, well, basically extrapolate, prognose how the system will behave in the future, you need to include some knowledge of the physics. And this is where engineering models come in. And so the idea would be to try and make the most of both worlds by developing models that are hybrid in nature. Of course, the problem in such a situation is that models that need to work synergistically with data, especially for our purposes, for the purpose of monitoring, should actually be able to do this to the degree feasible on the fly, feasibly in real time as data is attained. And in order to do that, you have to have representations that are computationally efficient and rapid enough to be able to be merged with data at such short time rates. So today I will discuss a bit on this within the context of structural health monitoring or condition monitoring. And I would like to start with explaining how to improve our prognostic or diagnostic capabilities by infusing some sort of structure into our representations. So here again, I show you this example. I'm staying in the same sort of use case, monitoring for wind energy infrastructure, where the type of data that you would obtain if you were to look at really low cost, again, acceleration information would look like this. This is over a time frame of about 10 minutes, and you see how the dynamics of the system is actually varying even within these 10 minutes. And this is because of the type of loads that the turbine is exposed to, but also because of the rotary dynamics of the rotor itself. If you were to expand on this and look at an interval of about a month, so beyond these 10 minutes, you would still see these variations, but now they're slightly different because the prevailing variations in this case come from the variation of the mean wind speed and the mean wind orientation. So we're talking about another scale of variability in this case. So in these systems, we know we deal with time periodic or time varying dynamics, but this dependency is twofold. In the short scale, it depends on gust, on rotor dynamics, but then in the lengthier time scale, it depends on the variability of the environment. And so we know about this structure, and the question is how to impose it in the data that we collect. So I'll show you here a treatment on an actual monitoring case study. And this is in a wind field in Germany, in Lübbenau, where we went to do this pilot project. We instrumented one of these turbines using our low-cost accelerometers in different locations along the tower of this turbine, different positions within the section, so that we can also get meaningful information about the way in which these systems deform. And then at the same time, we are collecting this SCADA information that I mentioned before, and these are readily available for wind turbine systems. They pertain to information about the environment and operation. And so we're talking about wind direction, speed, power, and temperature, many other variables as well, but these are perhaps the most defining. And whereas these are collected at very high frequency sampling rates, at about 100 hertz in this case, these are collected at averages of about 10 minutes. So they represent these different time scales that I mentioned before. And so the question is how, knowing that this structure exists, how do you impose it? In our case, we start from the vibration data, the higher sample data, and we develop time series models that are capable of representing the response of these systems. In this case, we're dealing with time-varying systems, so we will use time-varying autoregressive models. I will discuss a bit about this in what comes next. And in the second scale, we also try to condition these models on the slower variation of the environment. So we need to also take this second class of data into account. And by conditioning these to each other, we actually end up building a hierarchical, well, surrogate, as you would call it, model, which can be built with various different ways. You see here some of the ways in which we have chosen to structure these representations. But important for us, for the purpose of monitoring, is to develop this kind of model that claims to predict the response of the system. And once we establish such a model, then we can track the discrepancy between our prediction and the actual collected information and establish these quantitative, as I mentioned before, indicators of performance of the system. So I'll show you here an example that does this with a particular class of time series models that are of the parametric type, which are very attractive for anything that is a system that behaves in dynamic fashion. So let me show you examples of such models. Again, here is your chance to introduce structure into the system. So if you know that you're dealing with models that are possibly nonlinear, maybe you have a structural system that is experiencing yielding or geometric nonlinearity because of large displacements, then there exists a class of parameterized models that can quite comprehensively account for such behavior. If the system is non-stationary, then you could use a discrete wavelet transform to achieve the same goal. You could have a parameterized model that can track this kind of dynamic system. And if, like we do in this case, deal with the time-varying systems, then again, there exists a class of models that are parameterized, time-varying autoregressive models that you can actually use to model the response of the system as you expect it should behave. The second class of dependence on the environment, which was the slower evolution, can be taken care of by using these dependent structures. You can do this in various ways. We have experimented with polynomial chaos expansions or Gaussian process regression. And of course, you could also use neural networks. But the important thing is that now that you have a parameterized expression, then you can actually, in a second level, condition the coefficients of these models on these variations of the environment, which is what we try to do here. So here is again the spectrogram that we would obtain from this, the response, the acceleration response of this wind turbine tower, which varies in time. And you see here in the contour plot what is the actual measurement. And in the blue fitted lines, you see the performance of our time-varying autoregressive model, which indeed is successful in capturing this varying dynamics. If you were to naively just do a model analysis, which is a typical or favorite for dynamics representations, you would be fitting these constant dust lines that are not, of course, varying, that are not accurately tracking the dynamics of the system. And this, for us, gives us a benefit because we can more precisely track the response and better define indicators of performance of the system. So in the second level, this coefficient model, we, as I mentioned, use these different types of options, but of course, you're not constrained there. You could use anything that is your favorite, but the important aspect is to be able to develop this dependence model. And this is what we do here. We condition our short-term dynamics models on defining parameters of the operation and the environment, such as wind direction, the power, the RPM of the rotor, or the yaw, which is the orientation of the blade, of the nacelle of the turbine. And we're able to extract this sort of discrepancy indicator, which is what you see here. This is the error between our estimation, the simulated estimation of our model, and the actual measurement. And this, for us, serves as a type of indicator of whether the system is behaving as it should, or if there is something that we should be worried about. So this is the example. You have a training period that you need in order to train such a model of the system, and then a predictive period where you're actually predicting what the discrepancy is between the measurement and the actual estimation. And this is what brings us to the point of checking these instances where you're actually violating what you expect should be your performance threshold. This leads to the collection of certain outliers, which of course do not necessarily imply that there's necessarily something off with the system. At this stage, after the outliers are collected, we need to pass them through probabilistic analysis, a robust outlier analysis, which then allows us to construct such spaces where the performance is either within the prescribed threshold, so everything is behaving as it should, regardless of whether our inputs, our environments are within what we have observed or not, which is here, somewhere far off from the collected data that you gathered. So maybe here we have more adverse conditions, higher wind velocities, or different wind orientations. So here, in this case, as long as you're within the prescribed thresholds, we would be doing fine. Or there exist areas that are within the range of what we should be predicting, that you get a violation of performance. So here are outliers that actually should be of concern. Oh, so excuse me, actually this here should be what we have as a red alarm. And then finally in this area is what would be outliers that that are not easy to interpret because they actually occur at ranges that have not been met before. So here's where we should question actually our signalization system. So this is the point that I explained before, the separation in areas, everything is well performing. Here is the reason for concern. Here is an area where we're not confident about our estimation because the test statistic has not seen enough information to be able to robustly explain on whether this comes from damage, maybe structural damage, or just a simple environment that we're operating in. But this kind of signalization is very important for our operators and engineers because it translates the information from raw data that is not always easy to understand, and acceleration data point is not as easy to comprehend as a signal on whether the performance is as expected or not. So we use this red, amber, green type of signalization to deliver it to our operators and engineers. Now there is a step further that you could go, which is from this step here, which is more on detection. You could even be discussing localization of damage. And we have shown this, and many colleagues have shown this on toy systems like the one that you see here. This is a bridge type of system, another favorite for civil engineers, where we simulated different extents of damage, and where you assume that you have a network of sensors that are this time implemented, and we exploit the positioning of these sensors and some relevant metrics that have to do with derivatives of the measurements on these positions, the mode-shaped curvatures in our case. And it turns out you can actually quantify and localize damage quite well just from exploiting this positioning of the sensors. And of course, this is a very nice and educational example, but we have also done the same on actual bridges. On recent tests, we have actually went to the field. We have done control damages on bridges together with the Federal Roads Office. You see us here cutting tendons, something we don't advise, but for the purpose of research here, that was convenient. We have cut the tendons in locations of this bridge, and we have shown that you can indeed use the distribution of sensors, and you can localize damage. But this is a bit of the problem here. The most that we can do with these kinds of regimes is we can diagnose where damage or fault could exist. We can say whether it happened, which is detection. Possibly we could localize it if we have a good enough network of sensors, but we cannot say more, so we cannot prognose what happens next. And this is where you should bring physics into the loop in a way that goes beyond the structure that I showed in the beginning, which was just about dynamics. So here we want to bring structural mechanics into our simulation. And to do this in a way that makes sense for combining with data, we have to first discuss reduction. And so in our group, we have been developing different approaches, again, more from a civil engineering point of view on reduced or accelerated modeling for fracture, for plasticity and hysteretic phenomena, which are quite important in case you're dealing with plasticity, for systems that are experiencing large deformations or geometric nonlinearity, as you would call it, but also for systems that are assemblies of multiple components and where we use substructuring to try and accelerate our simulations. And so today I want to show you some more recent work from our group that tries to do this for reducing very expensive, very precise finite element models. So here is an idealized version of such a model, which of course comes with several degrees of freedom. What we would like to do is to solve the dynamic problem, but at a much faster pace than what your conventional finite element model would do, especially for problems that are nonlinear in nature. And so to do this, we try to exploit the principle of model analysis that you would use for linear systems, but now in a way that agrees with nonlinear analysis. So we try to extract what others would call nonlinear normal modes of a nonlinear system, and we do this using an autoencoder logic. So we pass the simulations of an expensive finite element model through the encoder step of an autoencoder, or you could here have also a variational autoencoder so that you can have a latent space of reduced features that are to the degree feasible uncorrelated to each other and approximate this concept of nonlinear normal modes. If you're able to do this and have this reduced representation, and you also have an inputting force to your system that is at some finite number of degrees of freedom, then you can build a regression, a dynamics model, but this time not for the expensive and full order millions of degrees of freedom, but just the latent space, the very cheap and comprehensive latent space that you have here. And you can do this using an LSTM or another recurrent neural network expression. LSTM is what we use here to obtain a regress model between an input force and this lower dimensional latent space. And if you do this, this means that you can solve your dynamics that is possibly nonlinear in this reduced order space. But then because you have this representation, the autoencoder, you can use the decoder step of this representation and go back from the reduced space into your original coordinates, which translate into this original model that you had. So what we did here is solve the dynamics problem, the nonlinear dynamics problem, but in this lower order dimensional system, which saves us a lot of time. Here is an example on doing this on a simulated data set that is quite relevant, again, within a civil engineering context. It's a shear frame building, which experiences nonlinearity in the hysteretic form. So there is a book-one model that describes the nonlinear behavior of all of these joints in this building. Basically what it means is if you have an earthquake or a load that takes you beyond the yield limit of these joints, then you will get a behavior that looks like this. And this is a nonlinear hysteretic behavior that is not necessarily very easy to model, especially when this is distributed within your system. Using the logic that I explained before, you can actually show that you can get a very good precision approximation of this nonlinear response in different degrees of freedom of this frame. And you can do this at a quite reduced time. So this is not always, it also depends on the example. So actually, if you had a bigger example here, it could be even more impressive. But just to give you a sense, this computation of about 5 seconds takes 0.8 seconds for this reduced order model in a non-optimized code, whereas 7 seconds, so actually more than the actual phenomenon in a conventional finite element software. We have made this benchmark available because we would like the community to use it for nonlinear simulations, so you will find it actually on our GitHub. But we also have a tutorial on how to make this kind of approximation for nonlinear systems that you can find uploaded on our page. Now, this kind of an approximation, of course, was trying to approximate nonlinear dynamics using a neural network approach, but another way to achieve this reduction that many researchers are also working on in this domain tries to maintain a more physical connotation in this kind of a reduced system. So again, I show you here this general equation that represents nonlinear dynamics. This is the equation that corresponded to this full field finite element model that I showed in the beginning that had multiple, maybe millions of degrees of freedom that you see here denoted as an order n. And where additionally, in this case, the complexity is that the model depends on some defining parameters. So I don't want to just have one finite element model. I want to be able to model a class of systems, maybe systems with different characteristics like stiffness properties or non-linear properties like yield, or also systems that have a dependence on characteristics of the input. For example, if it is an earthquake, that is particularly relevant for us, on the spectral and amplitude properties of this earthquake. So I would like to have these now parameterized reduced order models. And to do this, we will try to look for this reduction or use a reduction approach that respects the physics of the system. So it reduces the system, but it still leaves it, still allows it to live in a space of equations that agrees with the equations of the original system. But the difference is we're trying to express this space in a dimension r that is significantly lower to the original dimension n. And we do this using projection-based approaches. If this was a linear system, again, the easy equivalent to think about would be model analysis. But in this case, we achieve this through proper orthogonal decomposition. We obtain a reduced space by using simulations of this full order model, applying the proper orthogonal decomposition, and deriving a transformation matrix, a Galerkin projection basis that takes us to this lower dimensional space. Now, of course, because we discussed parametric dependence, this kind of a reduction has to be done over different sets of parameters. And this for nonlinear problems, and particularly problems that could be non-smooth, for example, problems that involve fracture, that I will discuss next, is non-trivial. It means that you have to efficiently separate your space of parameters, and you have to extract these Galerkin projection matrices in different clusters of the parameter space so that you can actually efficiently reduce your system. So you try to project this reduction in a manifold space. In recent work, we have suggested doing this in a fashion that combines a local and global type of dependence model. So we try to express the dependence in different levels, first on these projection matrices and then on the decomposition of these projection matrices. We found this to be a good compromise if you want to have a fast enough model that covers a large enough parameter space. Here is an example of how you would use these concepts on a rather simplified representation, but again relevant for us, because you could see it as a structure that is a support structure of a wind energy infrastructure, for example. So this is a 3D cantilever beam. It has a localized region of nonlinearity. We here assume parametric dependence on characteristics of the ground motion, which we assume has some temporal and spectral characteristics that define it. And additionally, we assume dependence on a property of the system, which is the yield stress, a nonlinear property. So we parameterize the ground motion. We use this principle of reduction, but we also here take it a step further because we're dealing with localized nonlinearities in work that has been done with our colleague Dane Quinn in the University of Akron and Adam Brink of Sandia. We try to take our original formulation of general Cartesian coordinates and decompose it in an ideal configuration that follows a linear equation of motion and a deviatory component that lives in a nonlinear space. And then we can more efficiently reduce our system because we use a different set of reduction bases for the linear part and a different set of reduction bases for the nonlinear part, which is localized. This is a trick that saves us a lot of time in our computation. And so at the end of the day, we can again have a reduced order model that offers a very good approximation of the high fidelity model. And here we have to say a very good depends on what is the level of accuracy that one wishes to obtain. For engineers, this can be quite different. For us, it always depends, or more commonly depends on the approximation on displacements and the stresses that can be produced by these models. And this is because these are aspects we're typically monitoring. So the strain, and indirectly the stress, and also the deformation in its dynamic sense. So here is a bit of the more important aspect in using these reduced order representations that are also physical. At the end of the day, you can always go back into your original finite element model, and at any point of the simulation, extract defining engineering properties such as strains, which again is something that we monitor, the strain on structural systems. And you do this at a reduced computation, again, feasibly near time or in real time or near real time, enough for us to be able to do diagnosis and prognosis. Now, the second aspect, because up to now I just showed the part of reduction and I've been discussing data and how you want to fuse this information with data, is to merge your models, your reduced order models, with this monitoring information. And so for us, this is called virtual sensing, again, in the structural health monitoring context, where you can imagine you have a structure. So here we show you an aerospace type of system, or it could be a wind turbine blade again. And typically what we do is we have a network of sensors on these systems that measure quantities like I mentioned before, could be acceleration or could be strain. And what we would like to do is to infer response also in positions of the system that could be critical, but are not necessarily monitored, either because we do not have enough budget, which is often the case, or because these locations are not necessarily easily accessible. Now that we have these models that can compute fast, that we can exploit, we can actually use these in conjunction with whatever sparse data we have from a system using a Bayesian filtering logic. So this is one of our most favorite tools for prediction in real time, and I will show you how this works in an example. But before I do that, maybe just to explain the overall concept of this virtual sensing. So imagine you have a structural system, and as I said before, you have some sort of information, could be sparse, could be incomplete and noisy, that come from different sensors that are deployed on this system. And so the goal is to extract or use this recorded data, even though you might have inputs, meaning loads, that are not necessarily known. Unfortunately for us, in most cases, we do not know the loads that are acting on our systems. We cannot exactly and precisely measure these. We do not have models that are necessarily configured a priori, so they usually come with some model discrepancy and error with respect to the parameters that are defining them. And here is the parametric uncertainty. And also, we do not measure all of the responses in a system. And I said before, this is what we would like to do. We would like to be able to estimate in a dense sense within our system, dynamic system. So to do this, we established this Bayesian filtering framework that serves as a virtual sensor and can extract quantities of interest, such as, for example, strain estimates in unreachable locations that can help us decide on the remaining fatigue life of the system. The challenges to this is that we're dealing with systems that are uncertain for the reasons that I explained before. We don't perfectly know what it is we have built unless we measure in some way. And even if we measure, there's the noise. Systems that are nonlinear, where the observations are scarce, and where the dimensionality is potentially large. And so I already explained that we could maybe tackle large dimensions because we can reduce our models, our dynamic systems. And if we do that, we can bring them in a formulation that looks like this, a reduced equation, dynamics equation of motion, which I won't go into the details, but it turns out you can always write in this form, even for general nonlinear systems. And additionally, an equation that describes the measurements, the observations that you get from this system. And if you have these two, it turns out that there exists an optimal Bayesian solution where if you could analytically solve these kinds of equations and integrals, you could have a prediction step where you use your equation of the system to predict what is your estimated response in the next point in time, and what is called the measurement update step, where you use that y vector, those actual measurements, to correct what it is you predicted so that it complies with your actual measured information. And this kind of logic, in theory, could be done in this sort of integral manner, but in reality, because of the complex systems we're dealing with, is not how we can accomplish this. Instead, we have to break down this problem, and we have to approximate these kinds of integrals by using sampling. And these are the types of filters we primarily prefer in our group, the unscented Kalman filter and the particle filter. These are discrete approximations of those analytical integrals where you have your state that is uncertain, that is simulated by using this discrete representation, these kinds of particles that you then propagate through your equation of motion. So you get the response of your system at the next point in time at those sampled locations. Okay, that's great. This gives you some sort of prior estimate of where your dynamic system will be at the next point in time. But then you don't know how far your estimation is from what you actually measure. And this is the step of the update, where you also take these particles and propagate them through your measurement equation. You figure out whether what you measured is close enough to what you predict is close enough to the actual measurement. And if not, you correct for it. And this is how you get this, let's say, data-informed posterior estimate that is a good approximation to your system that takes into account this information that is actually sparse data. It's not measurements at every location, but it helps you correct your estimate for the entire system. So let's try to see how this would work here for the purpose of damage detection. Again, it is an example that is inspired from aerospace structures as part of our SIMA Aero project. where we assume that there's a fuselage structure, maybe with a curved geometry, with some sparse sensors that are deployed onto the system. Here we have assumed that we measured strain or acceleration, but it could also be other types of information, as long as you can model the physics behind extracting this measurement. And so here the goal is to see if we can predict the location of cracks on this fuselage system, given that we would have some sparse sensors that are deployed onto this surface. The challenge here, well, I would try to follow exactly what I showed you before, the physics-based reduction approach that is parameterized again. And now my parameters are the characteristics of that crack, the location, the orientation, the positioning of the crack. But now the problem is that the underlying problem that I'm trying to solve is actually highly non-smooth. It's no longer a smooth, maybe nonlinear system. Depending on where your crack is located into that medium, you can get highly different reduction spaces, which makes this problem of parametric reduced order modeling non-trivial. So in order to tackle this, for the case of fracture, we have resorted to a trick. We have used mesh morphing, where we're using a reference or initial crack, and we use a reference mesh that we can actually manipulate and deform so that we can then express any other candidate location of a crack, because we're trying to solve an inverse problem here. We're trying to check where the crack positioning is. So we need different types of meshes, but the trick here allows us to use the same kind of reference mesh, the same type of nodes, and now our reduction matrices can more easily be constructed. And we can do this also for geometries that are curved. So we can have a morphed mesh that corresponds to this curved geometry of the fuselage. And once we have done this sort of manipulation, then it is easier to construct this reduced order model. So here you see an actual simulation. And the video might be a bit slower, but it's in fact in real time that you can have this reduced order model and its dynamic response obtained as you are actually tracking or monitoring a system. So now that we have this and it's fast enough, let's put it in the filter that I said before. Again, I don't want to go through the details, but only to show you the construct of such a filter that feeds observations, meaning measurements, with predictions that come from a model that is possibly nonlinear and parameterized, like the model I explained before. And it tries to see whether it can infer the position or it can infer the parameter vector, which in our case is these locations and the characteristics of the cracked geometry, in an affordable time, one that would allow us to do diagnosis on time. And so in this simulated example, this is what we show, that we are able to extract or soon converge in the actual value of the characteristics of these cracks, which are here located within that fuselage geometry. So here you see the actual estimation time, the initial random assumption of where the flow could be, and how the algorithm would converge soon enough on the actual positioning of these cracks. Here is more a comparison of how the models are actually performing. So you have the full order model. We have two full order models that we tried. One that is your classical finite element model, and of course takes a long time to compute. One that is a more efficient model, as you would typically do with a model reduction, for instance, which again takes some more reasonable but longer than real-time amount to compute. And then the reduced order model, which gives you a significant speed up with respect to these two more classical options. We have been using this kind of an approach on Bayesian filtering since 2010, and we have delivered a number of extensions and improvements to these algorithms, including prediction capabilities for systems that are, as I said, nonlinear in nature and where observability issues could arrive. We call it the discontinuous Kalman filter, and you could find more information on this on some of our published works. And we also have produced other schemes that are better at dealing with inference of parameters, which is oftentimes are desirable when we do damage detection, as for the case of the estimation of the parameters of the cracked geometries. So here we used constructs with mutation or other evolutionary operators for improving the performance of these filters. And this takes me to the very almost next to last part that I would like to discuss, which is tackling model discrepancy. Because what I've showed you here is great, but it has the quite strict formulation that we have we intended to do so, but we have imposed structure onto our formulation. We had a clear idea of what our models are. We tried to reduce these clear models. But the truth at the end of the day is that you cannot always account for the physics that is there for the systems that are operating as is. There is always something that probably was left unaccounted for. And this is the last part we're experimenting with. And this is our approach. So in this case, we assume that we have a system where, again, we record some part of the information at some sparse degrees of freedom. And we have some knowledge of the physics, as I explained in the beginning for the system, maybe a full order model that you reduced, following exactly the logic that I explained before. But we also know that there exists a part that we're not accounting for appropriately. And that's often the case for damping mechanisms, for example, in most dynamical systems. And so we leave this part to be learned from a neural network, more of a black box model that we do not claim to to have some sort of command on. And so here, by superimposing this sort of physics-based prediction and this learned prediction, we construct a model that capitalizes on physics, but is also flexible enough to learn what we are actually not able to model. Again, I wouldn't be going into the details of this, but the way in which we propose doing this in our recent work is to interfere with the already established deep Markov modeling approach. This is not something we have constructed, it's something that we use, and we manipulate it by taking its original architecture, and in the transition phase, so in the phase where in the latent space we're looking for the dynamic model of evolution of that space, we try to force it to have an aspect that is physical, that is really following our reduced order models, and another aspect that is eventually allowed to be learned. By doing this, by using this inductive bias, we end up predicting a latent space that is actually physical and no longer this agnostic type of space that a neural network would learn as a black box. We use this kind of a logic for condition monitoring or roadway infrastructure, or what you often is called the drive-by monitoring or onboard monitoring you could have also heard of. And here the idea is to try to use information from a vehicle that is traversing some piece of infrastructure, perhaps a road, perhaps a bridge, and from that information infer what is the response of the underlying substrate, what is the roughness maybe of the road, or what are the dynamics of the bridge. We did this on a simulated example, and here I just want to show you the influence of merging this physics-based and learned term by using a forced coefficient, in this case alpha. In reality, this coefficient is also learned. It's optimally derived. But just to show you the influence of physics, here is this problem of the vehicle that drives along a road of this kind of a profile, and we want to be able to infer that profile. And so we're using a reduced order model, a half-car model, which is typical to describe this kind of a vehicle. And then we try to, let me see if this will run. I don't know if you can press it, because maybe I have deactivated the video for this. Does it look like you could press the play button? Maybe not. Yeah, let me not take too long if that's not the case. It would be on this video here, the yellow line, yeah. Yeah, there you go. If you could press on it. It won't work, yeah. So what I wanted to show you here is that if you were to look at this, the mixing of this information would actually optimally behave when you have a coefficient at around 0.8. So when you're actually putting some knowledge of the physics, but you leave for something to be learned. Maybe a better way to show this that doesn't require then a video is here on this experimental validation, because always we need to experimentally validate what we claim for our approaches. This is a nonlinear system that is dynamic. It is the silver box model. It's basically an electronics device that produces this kind of an output that is a nonlinear function with a cubic nonlinearity of the input. It is a nonlinear type of model. And so we try to use this logic of having a physics-based term that captures the linear aspect of this response as we expected, and a learned term from a neural network. And this is the comparison of our approach, which is the, let's say, the physics-guided approach that gives you a latent space that very well agrees with the physical space of this problem. And this is the DMM approach, which also does what it should in terms of approximating the observation, which is the displacement, but then it doesn't learn the velocity, because this is a variable that is actually not monitored. So this black box approach will not necessarily give you a latent space that is physical, and this is what we're trying to here correct. And then just to end with this, I would like to show you what could be done next, because up to now I was trying to derive indicators of performance that stem from monitoring. One of the popular application areas for us, apart from the wind energy sector, is to do this on railway infrastructure, where, again, I mentioned already, we have instrumented vehicles in collaboration with the Federal Roads Office that usually gives us information in the form of acceleration at the axle box of these vehicles. We also have access to full, quite elaborate vehicle models, multi-body models that can be calibrated from measurements. But there, you can also have simplifying models, a reduced order type of model, as I explained before, that can be conditioned on the data and together can give you indicators of performance that can be used to direct decision support. So this is the part I want to close with, how to use this information for decision support. Just to show you how this works on the railway problem, these are an exemplary of our instrumented vehicle. This is where you would have the installation of the accelerometers at the axle box. It measures vibration. It can be combined with a reduced order model of the system, which follows the measurement and observation equation setup that I showed before. So again, here we use a Bayesian filter, a Kalman filter, to do our prediction. And we are inferring something similar to what I showed earlier for the vehicle, the profile of the rail in this case, the longitudinal level of the rail. And if you do that, then you can extract indicators such as this longitudinal level, which can be manipulated in different forms. Here by the SBB, there is a metric they compute out of this estimate, the fractal value, which is an indicator that actually deteriorates or actually lowers in value as the deterioration of the rail develops. And so depending on whether this indicator stands, the SBB or the engineers there would use this to prompt inspection of the rail to do remedial actions such as stamping and so forth. And so what I would like to show you is the idea of how to use this continuous monitoring information to support this kind of an approach where you want to take decisions on a structural system. So here is our deterioration process that is acting. And here is what you would get from monitoring. So every time you have an inspection, you get some sort of confidence of where your system stands. You want to be able to predict this on time so as to take the critical decision to improve the system when it makes sense so that you can extend its remaining life. And the way in which you can organize this problem when you have monitoring information is as a sequential decision-making process, where you have the state of your system, the condition, the indicators that I explained before, evolving in time. You have a set of observations that you could take. Maybe it's monitoring, and so it's continuous information, or maybe it's more specific actions, like a visual inspection you need to do, or a non-destructive evaluation that's more expensive and specific. And then some actions on what you need to do with your system. For the railway, maybe it's a minor action, like tamping, which is basically a local replacement of the infrastructure, or a complete renewal of the system. And everything comes at a cost. And so the aspect, or what you would like to do, is minimize this cost by taking the optimal set of observations and actions. And there's many ways to deal with the problem, and several researchers approach this using a Markov decision process, where the idea is that you're monitoring a system with perfect observation, so what you observe is really the truth. Or you can take a more relaxed approach into the setting and assume that what you observe is not necessarily the truth. Instead, it's actually uncertain. So there's only a limited amount of confidence that you can attribute to the observations that you take of a system. And for us, this is particularly relevant because what we measure is always noise corrupt and never perfect. And so if you do this, then this kind of sequential decision-making process includes an additional term that is really the confidence of your observations. Now, the problem is in real systems, it's not very easy to extract the models that tell you how a system deteriorates and what is the confidence of your observations. And so in our case, we try to use reinforcement learning to learn these kinds of constructs for real data. In our case, we do this for the SBB data, the Federal Roads Office. We use these estimates at the longitudinal level. We use logs that tell us what is the evolution of the state of the system, the track, when we observe different values of these fractal indicators that come from the data. And we try to build this deterioration model that basically tells you it looks like this. These are probability density functions that tell you how likely you are to transition from a stellar state or condition of your system into a deteriorated, more deteriorated, severely deteriorated state if you are to do nothing, so that's a deterioration model, or if you are to take an action, such as a minor or major renewal. And if you're able to develop these models, then using the indicators that I showed before that are uncertain, so they come with a mean and variance, you can plot your system in this space of possible conditions, and you can get an estimate from this partially observable Markov decision framework. You can get not an estimate, but a suggestion on what action to take next, and what would be the best observation to take to corroborate the state of your system after this action is taken. Once you do that, you progress through the management problem in what are called horizons, so the next state of your system, the next planning horizon, maybe the next 5 years in which you need to plan the maintenance of your system and take an optimal decision that would reduce the cost of this operation and maintenance problem. So with this, I would like to conclude, explain through these cycles or components of the chain of the structural monitoring problem, how data can actually complement our predictive and our diagnostic and prognostic capabilities, and how they can actually be exploited to our service, provided we can supplement them with constructs that are interpretable, that can help us maximize the information that come from this. And so with this, I would like to close, thanking those that were involved in this research, and of course, those that have supported it. Thank you very much.
Thanks a lot, Eleni. So there's time for questions. If you are following online, you can enter your questions in the chat, and we will relay them to the speaker. But let's prove that presential is better than online by taking questions from the audience. Martin first. There's a mic that will be handed out to you.
Many thanks for this very impressive presentation on all the tools, simulation and prediction that can be used. A naive question related with that. There is a lot of work in what you have to do that relates with the fact that you have localized sensors, and you have to position them well or be able to take advantage of knowing about the position. What about your expert opinion about if you take the wind turbines, a simpler approach where you would use a paint that would have a certain properties that are easier than the one of the structure that you have, where you could simply monitor cracks in the paint that would be predictive of what's happening in the structure behind it? Well,
actually, this is a great question, and if you're going to give me more sensors, I'm not going to say no. And what you're describing is what we call distributed sensing. So there are skins that you can use. There are fiber optics that we use as well. You can cover, kilometers of a bridge deck using a fiber optic system, and that's an even better situation. But even then, typically you cannot promise to cover the whole structure using these sensors, which is why we suggest using this. Actually, no, I should say that even in the case where you have this dense information, it's important to have a model that can help you understand what it is you're measuring and then extrapolate what it is you predict. But of course, everything would be easier, and this is the desirable, to try and use technologies that can give us even more information if feasible. As part of one of these projects for wind energy systems, it's called the Aerosense Project. We're developing a type of sleeves for wind turbine blades, exactly because of the logic that you here discuss. Again, it would be more localized, but still would cover a broader area than what localized sensors would, and give us also information about pressure and distributions that are more valuable than just very point-wise information. This is also important.
Thanks. Other questions?
Kalimera, Eleni. Thank you very much for your impressive presentation. So I understood that you have your physics-based models and you are using them to do simulations based on analytic models that you have, and then you collect real-time data using sensors. So are you using this data also real-time or offline? to combine them with the simulations?
Yes, I mean, if you're asking me, the research we do focuses more on real time, or what we call near real time, because sometimes you don't need to be as fast, let's say, as fast as strict real time. You would be okay predicting in a close enough interval, and maybe you would call it offline or near real time, it doesn't matter. But depending on the goal that you have, you can use this information in different ways. Actually, it is also okay to do an offline updating, as some would do, if the amount within which you, the amount of decision time you have allows for this. But for some cases, particularly wind turbines, if you imagine you have a lightning strike, you don't really have what we would call offline estimation time. You could have near real time to decide on whether to send someone there, whether to power down the turbine and so forth, but you need to be fast. And so these are more of the applications we target, and probably also you could relate them to aspects of control. So there as well, you need to have a decision that is as fast as the, on the fly, essentially, as you get data.
Thank you. Over here, Alfie.
Thank you for this very great talk. I have a little question concerning your use of nonlinear model order reduction when you try to detect the location of the crack on the airplane, say. I'm wondering which kind of a priori information you need in order to locate your structure.
Yes.
As far as I understand, you are assuming that the parameters are describing indeed the position of the crack.
Yes, so because the parameters describe the position of the crack, the claim here is that you don't need to know where the crack actually is. But of course, you have made a number of assumptions until, at least for this simplified problem that I showed here. First of all, that it's a linear crack, which is not necessarily the case. Secondly, that it's not propagating. It is a static crack in what I tried to predict here. But of course, these are relaxations that you can start building once this framework exists. And this is what we would like actually to do. Another assumption that has been made here is that I have actually a model that more or less describes quite accurately the pristine geometry, which might also not be the case. And that's why you see all of these aspects of relaxation in the piecewise framework I've tried to put together so that we can account for model discrepancy, so that we can account for different type of information that can corroborate our system. For example, for fracture and detection of cracks, perhaps the best source of sensor data to use would be guided wave-based data, not necessarily just strain and acceleration and vibration information that maybe do not have the high frequency content that is required to find very local and very small cracks. So there are aspects to the simple example that I showed that need a lot of elaboration to bring them into a general context that would fit all, let's say. But that's the challenge and the nice thing in trying to look for these solutions.
Fabio?
Yeah, thank you. Hi, Eleni. Thank you for the very inspiring talk. My question is very much related to Alfio's one. When you do this crack detection, so I understand that you have a model that somehow parameterizes the possible location of the crack. So in a sense, you're, if I understood, you're trying to interpret the discrepancy with the data by a presence of a crack in a certain location.
Yes.
So I was wondering if, thinking more broadly, there might be other causes of discrepancy with the data. So how this should be managed? I mean, one could think of have a less ambitious goal of try to do anomaly detection, so saying something is getting wrong, or a more ambitious one trying to infer also on the cause of this discrepancy.
Actually, you're absolutely right. And this is, in a practical setting, the way in which we approach this. So we have a recent paper out where you structure this framework in exactly this kind of way. First, the easiest thing you can do is detection, and that can be data-driven. That was my point in the beginning. And so usually you would activate these mechanisms when you first do detection, and maybe even, if you have this network of sensors, a possible localization. And then when you start understanding the phenomenon, then you can go into a more, an activation of means that are more specific, such as this one, to try and see if you can do something as refined as a crack detection. And probably you have to do this in cases where you cannot just simply go there and look. Maybe it is fuselage again, or something that you need to detect over a flight. Or maybe it's an unreachable location of a bridge somewhere upon a structure. So for these cases, you have to follow the reasoning, which is the logic that you describe now. Go from the simple goal of detection, possibly roughly localization based on where it is that you obtain most of the discrepancy, to very precise characterization. And all these are the structural levels of the SHM hierarchy, as once defined also by Ritter as well. We need to be doing this, if practically done, we need to do this in this sequence, really. So you shouldn't go from the beginning for solving everything. That's also not so realistic.
Thank you. One more.
Thank you very much for your very insightful presentation. I just have a question related to some of the, like 10 years ago, technology using, for example, infrared sensors or holographic methods. Would it be possible to combine those different methods in addition to the sensors in order to identify like cracks or sometimes like vibration within the models to retrain, like to make it more efficient? I know those technology were in the past, like 10 years ago, infrared and also holographic imaging. But with the sensors, would that improve the modeling learning?
Definitely, and this is what many today would describe as an augmented reality type of model. So you could gather all the information you have. In fact, for the SPB case, because there is a quite comprehensive digital platform that gathers information from non-destructive evaluation of diagnostic vehicles, from high-resolution images of the track, vibration data that we gather, we try to do exactly this, to combine these in order to get more informed labels, because in many cases, it turns out to be, I mean, you cannot avoid it in damage identification. It comes down to a classification problem for which either you have labels, maybe coming from experts, maybe presented by platforms that are virtual, for example, or maybe you do not have labels and you have to exploit other data you have, like image information and automated processing on this. So it's exactly the synergy of these different tools that now should be brought to life to improve the capabilities. You're completely right.
All right. If there is no other question, let's thank our speaker once again. We now have a short break in the hall just in front of the room where there will be ample opportunities to drink coffee, network, and there's also a set of posters for you to see and discuss. Thanks a lot for being here. Presence beats Zoom 1-0 in terms of question this morning.